Okay. In the last lecture, we had stopped here. We had decided that this epsilon ij is a small strain tensor, which is derived from the Green-Lagrange strain tensor, which is a more general concept. We dropped the terms involving products of the gradients of the displacement, and then we ended up with the symmetric strain tensor, which is basically just a geometric description of changes in lengths and angles. Okay, it's a geometric description of the deformation. Now, how do we handle this? Uh, we write generally the displacement as we have done before, u as, let's say, ui ei, right? This is how we do it in Cartesian system. Sometimes, uh, especially in two-dimensional problems, we may not always write u1, u2, u3. We may write u, v, w as the components. Then we will write u as u e1 plus v e2 plus w e3. Okay. And then we have the gradient operator, which in Cartesian system is del del x1 e1 e2 e3. We know this. And then when we do gradient of u, we get a second order tensor where we have these dyadics e1 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 e2 and so on. As we multiply nabla with u, we have a vector representation of u, we have a vector representation of nabla, multiply the two together. Remember that in e1 is we don't need to take derivatives of u1 because this is a fixed basis, so we will get del u1 del x1 only. So doing all that, this is what we will get. We have done this before, and finally, if we write it in indicial notation, we will write it as del ui del xj ei ej. Now, sometimes it is necessary to write this as in a matrix form. When we write this in a matrix form, uh, especially when we are not using indicial notations, we may want to write it as in a matrix form. Then we mentally map x1, x2, x3 to uvw and x1, x2, x3 to xyz, and this is how we will write it. This matrix is del u1 del x1, so del u del x, del u1 del x2, del u1 del x3, del u2 del x1, del u2 del x2, del u2 del x3, and so on. So u1, u2, u3 replaced by uvw, and x1, x2, x3 replaced by xyz, and that will give us this particular matrix representation of the Cartesian components of the strain. Now, to do gradient of U transpose, we simply have to change the order of U and nabla, and that will basically mean that that will basically mean that you now have del uj del xi ei ej as your components. Again, doing the same mapping, the transpose will be del u1 del x1, del u1 del x2, del u1 del x3. This was the row in gradient of u. Now it has become a column. Similarly, this has become a column. This has become a column. Add the two together. Nabla u plus nabla u transpose, and nabla u plus nabla u transpose, and you get a symmetric second order tensor, which is oh, don't forget the half in front. So half nabla u plus nabla u transpose is simply the addition of this tensor, this matrix representation of the tensor, with this matrix representation of the tensor, with the half in the front, will give you the small strain tensor. So this is how it will look like, the small strain tensor. This is how it will look like. The first one will be del u1 del x1, that's epsilon 1 1, epsilon 1 2, epsilon 1 3, epsilon 2 2, epsilon 2 3, and epsilon 3 3. The rest of it is symmetric because we have already seen that epsilon ij, if you switch j and I, the meaning of this right hand side does not change. So it's a symmetric, the components are symmetric, so it's a symmetric second order tensor, which can be represented as a symmetric 3 cross 3 matrix whose components in the Cartesian system are going to be like this. Now, if you write those components out, and you have seen this in your ESO 202 course, if you write those components out, epsilon 11 we call epsilon xx, yy is 22, zz is 33, 1 2 1 3 2 3 and so on, and these are the components where we have replaced u1 u2 u3 by uvw and x1 x2 x3 by xyz. This is what you would probably find in Crandall and Dahl. Out of this, the first three, 1 1 2 2 and 3 3, we call them as normal components of strain, whereas 1 2 1 3 and 2 3 we call them shear strains. So these are given different names because their physical representation is different. Again, you have probably seen this in your MOS course, but I'll just repeat this in 2D. It's not very difficult to visualize. It's important to realize that these three components, the first three components and the last three components of the small strain tensor, have somewhat different connotations physically. Before that, we can do this nabla times u like we have done a few classes earlier. This nabla times u in, let's say, cylindrical polar coordinates. In cylindrical polar coordinates, your displacement is given in terms of r component, theta component, and z component. And the basis vectors are er, e theta, ez. We have done this before again. And then when you take this nabla, nabla has a particular form in the cylindrical polar coordinate system. And when you do this nabla times u, you have to remember that er and e theta are not independent, are not fixed basis vectors, but they are themselves functions of theta. So when you do this, you have to carefully take the derivatives with respect to theta of the base vectors themselves. And if you do that, and if you write the strain out, this would be the 6 independent components of the strain tensor that you would get in the Cartesian, in the cylindrical polar coordinate system. So this is in the Cartesian system, the 6 components in the Cartesian system, and these are the 6 components in the cylindrical polar coordinate system. So it would be good if you can remember this, but even if you cannot remember, this is the way to figure it out. Once you are familiar with the way in which this nabla operator is handled in cylindrical polar coordinates, you should be able to derive this, and I strongly suggest that you do that and make sure that you get these components out as the 6 components in the cylindrical polar coordinate system. You can try it out in spherical as well. I don't have the spherical equations here, but if you are interested, I can post them. Okay, let us do a problem here. So the problem is, this is a motion. This is some kind of a motion. Don't worry too much about visualizing it, but it is a 2-dimensional motion because small x3 is equal to capital X3. So there's no motion along the 3 direction. So I have taken a 2-dimensional motion because that's possible to draw on the plane, and it's easier to understand. So once you have this motion, it is easy to calculate the deformation gradient. So the way we do it is like this. So I have the motion, which is small x1 equal to capital X1 plus k capital X2 square t square. Small x2 is equal to capital X2 plus k capital X2 times t, and small x3 is equal to capital X3. So I should remember that Fij is del small xi del capital Xj. So you can do it as a dyadic in the dyadic way, or you can write its components as a matrix in the Cartesian system. So all you have to do is calculate del x1 del capital X1. That would be your F11. That would be 1 del small x1 del capital X2 would be 2k x2 t square. Del x1 del x3 would be of 0. del x2 del x1 from here would be 0. Del x2 del x2 would be equal to 1 plus kt. This then x2 x3 will be equal to 0. With for small x3 everything will be 0 except del x3 del capital X3, which will be equal to 1. So this will give you your deformation gradient, and again remember that this is equal to del xj of x small xi is ui plus capital Xi. So that gives you del ui del capital Xj plus delta ij. This is what, and if you write it in vector notation, f is equal to nabla 0u, the 0 signifying that you have capital X here, plus I. So once you have got f, the components of f in the Cartesian system, you subtract I from it and you get the components of nabla 0u from there. And then I know that the large green Lagrange strain tensor is E half of nabla 0u plus nabla 0u whole transpose plus nabla 0u times nabla 0u transpose, something like this. So this is it. Once I get nabla 0u, I plug it into this and get the green Lagrange strain tensor. If I now want the if I now want the small strain tensor as well, so I will simply do this, we drop this term, and remember this and this are not different. When you have neglected gradient of u, these two things are not different, but since we have nabla 0u handy, we just use this in place of in the small strain tensor as well. This and this would basically be the same. Okay, now we know that the change in squared length dx squared minus d capital X squared, the change in squared length is given by E times d capital X, take a small vector dotted, pre-dotted with d capital X. I think there's a 2 here. So this gives the change in the squared length. Okay. Now what we are going to do is, we are going to calculate all this. For this particular motion that I have taken, I will calculate the deformation gradient. Then I will go ahead and calculate this quantity. And then I will calculate this whole tensor and this whole tensor. Okay. So I can do that in terms of components in the Cartesian system. After doing that, I'm going to take a line which is oriented at 45 degrees to the x1 axis, so x1, x2 axis. I'll take a small segment which I'll call dx. Okay, this segment is about 0.1 units long. I've just taken it to be a small line, and I will do this operation. So this is 0.1 times a vector which is oriented at about 45 degrees, to the x-axis. So this is 0.1 into some vector that gives the orientation. This is the same, and this I have the components of this I have calculated from the motion. So I'm going to do this operation, and this operation would give me the change in squared length of this line. Remember, this I have taken to be 0.1, so this is 0.1 square to start with, and this will be the deformed length. So the change in squared lengths will be given by this operation, and I will compare the change in squared length that I get from here and here as the motion proceeds. As the motion proceeds means I'm going to increase time from 0 to some value. As the time proceeds, you will see how the points displace and how this particular straight line that I have taken uh, changes in shape as time goes on. So let's see that. Okay, so this is what I was describing. So I've calculated f, then I subtracted I from the f, I got nabla 0 u. I then calculate the green Lagrange strain tensor. I do this in MATLAB, I don't do it by hand. I calculate the small strain tensor, and for the small strain tensor, remember this and this are identical. And now I take a unit square and several points on the unit square. That's what I'm going to show you in the following animation. And then I take a small line segment which is initially inclined at 45 degrees and has a length of not 0.1, it's root 2 times 0.1. That's what I have taken. And it's oriented 45 degrees to the x1 axis. And in red, you will see the deformed length of the line according to this tensor, and in black, you will see the deformed length in this tensor. So what we expect is that as time goes on and as the deformations become large, the effect of this square term will come into picture, and then the lengths predicted by using this and the lengths predicted by using this would start to differ. That's what basically you will see. So here is the square which is deforming according to the motion that is given, and these are the two lines, and the red is the change in length due to the small strain tensor, and the black is the change in length due to the green Lagrange strain tensor. I'll play it again. So it plays again. So you see initially they are quite small, but then the deformations become pretty wild, and as a result you have quite a bit of difference between the black line and the red line. The dots are just points on the square which are being mapped according to the motion, and it's deforming because time is going from 0 to some value. We're starting with a square with several points inside the square. This is what we are starting with, and then as the motion proceeds, we are getting different predictions from the green Lagrange strain tensor. The only point that I want to make from this animation is that the small strain and the green Lagrange strain are virtually identical when the deformations are small, gradients of displacement are small. But once that stops being valid, like what you see now on your screen, once that stops being valid, then you need to take those cross terms involving products of displacement gradients into account, and you need to make a distinction between the deformed configuration and the undeformed configuration. You need to make a distinction between nabla 0 and nabla. All those things we will forget in this course from now on, and we will assume that this kind of deformation is something that we are not concerned with. We are concerned with deformation that is close to this situation, maybe up to this. Here the differences are becoming too large for us to be comfortable, and we are not concerned with these things. We are concerned with the deformations that we saw before the deviation happened. Okay, now with that behind us, we are going to forget the green Lagrange strain tensor till you have a chance to do a continuum mechanics course. If you get a chance, we will be satisfied with the small strain tensor from now on. So what are the meanings of the components of the small strain tensor? So what we have done so far is try to describe the geometry of the deformation, and this is how we have done it. So this is a body sitting in a 2D space for simplicity. It could be 3D as well, And then we have gone to a point denoted by small x and taken a small box with edges parallel to the x1 and x2 directions. Okay, small box with lengths dx1, dx2, and then somehow deformation of the body occurs and the body goes into a deformed shape. As a result, this small box that I had drawn on the 2D plane assumes a different shape as well, which is given by the dashed lines. My strain tensor somehow describes this dashed box with respect to the box drawn with solid lines. Okay, let's blow up the rectangle. So ABCD is our rectangle. AB is parallel to the x1 axis, AD is parallel to the x2 axis, and it deforms to A prime, B prime, C prime, D prime. Now, A is located at the head of the vector x, the position vector, and these edges are dx1 and dx2. So A suffers a displacement in the x1 direction of u1, which is a function of x1, x2, and we assume that it's a smooth, well-defined, continuous function of x1, x2, so that the x displacement of B is given by x2 remains the same, x2 of A and B are the same, but x1 increases by dx1. Similarly, A suffers a displacement of u2, which is again a smooth function of x1 and x2. It could be x1, x2, x3, but I'm taking x1, x2 for the sake of simplicity. So D is just dx2 distance away. Its x1 is the same, but x2 is just dx2 away. So D would suffer a displacement of x1 comma x2 plus dx2. u2 would be this. Now, you can use the Taylor series. If you use the Taylor series and stop at the first term, then remember, in going from A to B, x2 does not change. So Taylor series would involve a derivative with respect to x1 times dx1. That's the distance between A and B. Similarly, this angle would be du2 dx1. So in going from A to B, in A to B, you have varied x1, and this distance from here to here is given by u2. So this distance is del u2 del x1 times dx1. So this is the distance. This is the difference between the u2 of A and B. Similarly, this is the distance between the u2 of C and D, A and D, u2 of A and D, and again you can apply the Taylor series and stop at the first term to u2. As you go from A to D, you have varied only x2, so only dx2 comes here, and the derivative that is involved is del u2 del x2. So you can do this mentally, and this is how the geometry would look like. Now, if you look at this a little harder, we can call this angle alpha. So the angle alpha would be this length. This, remember, is the uh, difference in u2 between A and B, and this is the difference in u1 between A and D. Okay, so this divided by this height, would give you alpha, and this divided by this distance here would give you beta. Okay, now let us try to see what is A prime B prime minus AB divided by AB. So this is the changed length of AB, and this is the initial length of AB, which is equal to dx1. And what we are trying to see is what is A prime B prime minus AB divided by AB, where AB is dx1. If you do this and you neglect the terms that contain squares of the displacement gradients, because displacement gradients, remember, are small, you would see that this quantity A prime B prime minus AB by AB is simply equal to du1 dx1, which is our definition of epsilon 1 1. So epsilon 1 1 represents the change in length of a line segment which was initially along the one direction after deformation. The relative change in length of the line after relative change in length of the line is a prime b prime. This is the change length minus the initial length divided by the initial length. This is the relative change in the length of a line which was initially along the x1 direction, gives you epsilon 1 1. Similarly, relative change of a line which was initially along 2 direction will give you epsilon 2 2. That means epsilon 2 2 will be given by a prime d prime minus ad divided by ad. If you do that, you will simply get del u2 del x2, which was our definition for epsilon 2 2 to start with. Now let us look at a shear angle. So let us look at this quantity gamma 1 2, which is pi by 2 minus pi by 2 minus alpha plus beta. And remember, alpha is del u1 del x2 and alpha is del u2 del x1 and beta is del u1 del x2. So if you plug that in, you will see that this quantity pi by 2 minus this angle is equal to, again neglecting some terms, del u1 del x2 plus del u2 del x1, which is simply twice of the quantity epsilon 1 2. Remember that we according to our tensorial definition, epsilon ij is half u I comma j plus u j comma I, and epsilon 1 2 therefore is half of u1 comma 2 plus u2 comma 1, which is half of del u1 del x2 plus del u2 del x1. This is it. So this is our epsilon 1 2, and what we found as gamma 1 2 is twice of epsilon 1 2. So gamma 1 2 is called the engineering shear strain. Gamma 1 2 is called the engineering shear strain. It's a twice of the tensorial shear strain, and epsilon 1 2 is the tensorial shear strain. Now what gamma 1 2 represents is the change in length. Gamma 1 2 represents pi by 2 minus this angle. So what gamma 1 2 actually represents is change in length of between two lines, one oriented along the one direction, one oriented along two direction, from 90 degrees. Obviously these two lines initially have an angle of 90 degree. The change in angle from 90 degree, which is alpha plus beta, is represented by gamma 1 2, and that in turn is twice the shear strain epsilon 1 2. So the shear strain represents half of the change in angle between two lines which are oriented along the one and the two directions. That's what epsilon 1 2 represents.